Hi everyone, welcome to Om Learning Lab. This video is the second part to the solution of this arrangement problem from INMO 2050. In the first part, we solved this problem using a pure mathematical approach. In this part, we will be using recurrence to build a more robust and a general solution to this problem, and we will be implementing that solution in code using bottom-up dynamic programming. Now, this video is a standalone video, so this can be watched separately and everything will be just fine. However, I would still recommend people to go back and watch the first video to build an intuition about this problem, to get a flavor of the problem. I have linked the first part of the video in the description, so interested people can check that out. Without any further ado, let's solve this. Now, here in the original problem, there are 4 basketball players and there are 7 passes. And of course, ball is passed from one person to a different person. And here the number of passes, if I represent the total number of passes as n is number of passes and m is the number of players, let's say. So originally this number of passes was 7, number of players was 4, and we solved it and the answer had come out to be 546. Please remember that this answer we had got in the first part of the video. We want to generalize this. We want to build a solution which can handle n passes at m players, not just this particular case. How do you do that? We use something called recurrence. Now, let's pay attention carefully. If we have n number of passes, how many players will be there in between? There will be n minus 1 spaces in between. Let's say we have A. After one pass, let's say it goes to player number x1. After the second pass, it goes to x2. So on and so forth. After n minus 1 passes, it will go to xn minus 1. And then we have the nth pass, the final pass, back to A. Right, so we have these many positions in between. Now, if I represent the answer after n passes, after n passes, let's say I call it some variable answer after n passes, then it's not difficult to observe that the total number of ways A is going to get the ball after n passes will be same as total number of ways in which these m minus 1 players will receive the ball, excluding A of course, receive the ball after n minus 1 passes. That is, let me call these players as P1, P2 up to Pm. So let me call these m players here as player 1, P2 up to Pm. And for the sake of completeness, let's call the mth player, let's say that player is A. So the mth player is A. So there are m players including A, right? So just without any loss of generality, I'm assuming that the mth player is A. Now, the number of ways A can receive the ball after n passes is same as the number of ways P1 to Pm minus 1 can receive the ball after n minus 1 passes, because A can receive the ball from P1 or from P2 or from P3 all the way up to Pm minus 1. Hence, all these ways of receiving ball after n minus 1 passes will be added, like the number of ways P1 receives after n minus 1 passes plus number of ways P2 receives after n minus 2 passes, so on and so forth up to Pm minus 1. Sorry, this is n minus 1 passes. Let me define this as some variable called ways of n minus 1. Just to reiterate what I said, the answer after n number of passes, how many ways can A receive, is same as the total number of ways the remaining players P1 to Pm minus 1 can receive after n minus 1 passes. because A has to receive the ball from either one of them. Remember that in our convention we have chosen PM to be A. Now this part should be clear. This is ways of n-1. I'm basically taking this summation of all the different ways players number 1 to m-1 can receive the ball as a variable called ways. I'm adding all of them up and storing them in a variable called ways. So this is ways of n-1. So answer of n is total number of ways of n-1. This is the first part. Now we need to observe how ways of n-1 behaves. Ways of n-1 is basically how many ways p1 to pm-1 are receiving the ball after n-1 passes. Now if we look what happens at x of n-2, I mean, how can P1 to Pm-1 receive the ball after n-1 passes? Either they receive the ball from A, that is, they receive from Pm. If they receive the ball from Pm, like P1 can receive from Pm, P2 can receive from Pm, all the way up to Pm-1 can receive the ball from Pm. So, ways of n-1, like the total number of ways they can receive the ball after n-1 passes, one component is they receive the ball from A at x of n-2. If they receive the ball from A at x of n-2, it will be m-1 times, like each player can receive the ball how many times? The number of times A would have received the ball after n-2 passes. Basically, that would be m-1 multiplied with answer of n-2. Why is that so? Because if at x of n-2 I have A can receive ball in several ways. Basically, it will be answer of n-2 ways. And for each such way, the ball can be transferred to P1 or P2 all the way up to Pm-1. Hence, all those ways, answer of n-2 ways will be multiplied with m-1 for each of the players. That is one possibility for ways of n-1. What is the other possibility? That they are receiving the ball from one among themselves. They are not receiving it from A. That will be a little tricky to understand. So let me choose a separate color and try to explain that. So let's observe here. Let's say at x of n-1, let's say P1 was receiving the ball. Now if P1 is receiving the ball, who can be at x of n-2? Please note that we have taken care of Pm, that is A. We have already taken care of A. Each of them can receive the ball from A in answer of n-2 ways. This is the contribution we have already taken care of. We are talking about the other case, that is if they are receiving the ball from one among themselves. Now if x of n-1 is P1, x of n-2 can be something from P2, P3 all the way up to Pm-1, right? If x of n-1 was P2, this could have been P1, P3 all the way up to P of m-1. This can be extended all the way up to P of m-1. If it was Pm-1, this would be P1, P2 all the way up to P of m-2. And from whom can it receive the ball? It can receive the ball from this set, excluding himself and A. Now if we add all these ways, so these are the total possible cases, right? Either x of n-1 was P1 or x of n-1 was P2 or all the way up to m-1. So if we add all possible such ways when they are not receiving the ball from A at x of n-2, this is the total possible cases. And interestingly, if we look at any particular variable here, let's say P2, how many times is P2 appearing here? P2 will appear all the times except when it was himself at x of n-1. When P2 was at x of n-1, it cannot receive the ball. But other than that, in every case, it can pass the ball. It can pass the ball to P1, P3 up to P of m-1. So P2 will be present how many times? m-2 times. Similarly, you take P1. P1 will also be present m-2 times. P1 can pass the ball to P2, P3 up to P of m-1. Except himself, when P1 was at x of n-1, it will be present all the times. So it is present all the times. And same will be true for all the remaining. For example, P of m minus 1, it will also be present m minus 2 times. The only case it will not be present is when itself, it is that x of n minus 1, it can self passes are not allowed. It has been clearly mentioned in the problem. It has to be passed to a different person. Self passes are not allowed. So each of these contributions will be m minus 2 times. Like P1 will contribute m minus 2 times. So P1 at n minus 2, how much ever it had, all those contributions will come and it will come m minus 2 times. Same for the remaining, m minus 2 times P2 will also contribute from n minus 2. So on and so forth. So we can take m minus 2 common and basically we'll have P1 at n minus 2 plus P2 at n minus 2, so on and so forth, which I have defined as this ways variable. So this will be total number of ways at n minus 2, right? I'll go through this one more time because this might be little challenging for people to understand. What happens here is at x of n minus 1, we have P1 to Pm minus 1. Either they receive the ball from A. If they receive the ball from A, each of them will have access to answer of n minus 2 ways. Right? All those ways A can receive the ball after n minus 2 passes. Each such way can contribute either to P1 or P2 up to m minus 1. Hence, this has been taken care of. Now, other than that, they can receive the ball from within this set. If they are receiving the ball from within this set, if at x of n minus 1 we had P1, it can receive the ball from P2, P3 or up till P of m minus 1. Similarly, if it was P2, it can receive from P1, P3 all the way up to Pm minus 1, so on and so forth. And if we look at the contributions, each of them have at x of n minus 2, every element will repeat m minus 2 times. P1 will be present m minus 2 times. Only time it will not be present is when itself it was at x of n minus 1. Same happens for the remaining, all the rest of them. So when we add the contributions at n minus 2 from P1, P2 up till P of m minus 1, we can take m minus 2 common. And the remaining part, P1 at n minus 2 plus P2 at n minus 2, so on and so forth, we have already defined a general variable, right? So the contributions from P1, P2 up to P of m minus 1 at any given position after any number of passes, it's basically a variable called ways. So that is ways of n minus 2. So hence, here we have ways of m minus 2 times ways of n minus 2. Right. So, in short, if we summarize the entire thing, we have answer after n passes is same as ways of n minus 1. So, you can write it here. Answer after n passes is same as ways, that is total number of ways P1 to Pm minus 1 can receive the ball after n minus 1 passes. And this, in turn, we have broken it down to come out to be m minus 1 times answer after n minus 2 passes. Apologies for that. Let's fix that. Answer after n minus 2 passes plus m minus 2 times ways, that is how many ways P1 to Pm minus 1 received the ball after n minus 2 passes. Right? That's the contribution, right? If P1 is receiving from P2, P3 up to Pm minus 1, it will receive for each such way. For each way P2 received the ball after n minus 2 pass will contribute to P1. And similar idea follows. So this is what we have. We can in fact convert everything to a single variable now. We don't need to have answer and ways because basically answer and ways are related. However, for the sake of clarity and ease of implementation in code, I will still keep them as separate variables. So answer after n passes is basically m minus 1 times answer after n minus 2 passes plus m minus 2 times ways after n minus 2 passes. How many ways the remaining people can receive it. And we can have initial values answer after 0 passes. There is no pass. Has to be 0. Like if there is no pass, there can be no answer. Answer after 1 pass. Self passes are not allowed, so it will also be 0. Like we have A cannot pass to himself. So after a single pass, also answer will be 0. And if we talk about ways, how many ways are there? If ways means how many ways P1 up to Pm minus 1 can receive, right? So if we have A here and there is a single pass, we have P1 up to Pm minus 1. How many ways are there? So A can give to P1 or P2 up to M minus 1. So ways after when one pass will be M minus 1. These are some initial values that we need, because when we're using bottom-up TP, so what happens in bottom-up TP is we initialize these simple values which you can compute by hand, and then we write a code for it and let the machine do the rest. We'll just apply this recurrence logic. We'll just put this formula and we'll let the machine do the rest for us. We'll just use these initial values. Okay. Let's try and implement this in code, and once the code has been implemented and we verify that everything is correct, I'll just go over the solution once again, briefly. Let's implement this in code. Let me go to VS Code. Okay. So let's have a print statement like enter the number of players. So this is some input that we'll take from user. And let's declare some M, C in M. So this is the number of players. Then let's take another input. Let's call that enter the number of passes. Okay. So we have the number of players, we have the number of passes. What we do next is we need to store them somehow. So I'm going to use a vector here. This is basically an STL implementation of the array data structure. Let's call answer, and we have another variable called ways. So what we are doing, what was the formula? M minus 1 times this, M minus 2 times that. Okay. So ways of 1 will be M minus 1. That was the initial value that I was talking about here. And by default, everything is assigned 0, so I don't have to explicitly write 0 for the remaining cases. Then I can run a for loop. I can run a for loop from 2 to, I guess, this. And then I use the recurrence. So ways at any position is M minus 1 times what was the relation? So ways at any position at n minus 1 is M minus 1 times answer at the previous position plus M minus 2 times ways at the previous position. So ways at I will be M minus 1 times answer at I minus 1. Please notice I'm just shifting the indices. That's not going to affect the recurrence relation. Plus M minus 2 times ways at I minus 1. And of course, answer at ith position will be number of ways at I minus 1. Because, and I'm just basically doing this implementation, whatever we derived here, right? So answer after n passes is number of ways after n minus 1 passes. That's what I have done here, right? This part. And I have kept the recurrence relation as it is. Like ways, number of ways are at any, after any number of given number of passes is m minus 1 times answer 1 less pass plus m minus 2 times multiplied with the number of ways before 1 pass, like 1 pass less. That's what I have done here. Having done this much, of course, the final after n passes answer of n will be ways of n minus 1, because we have not kept that in the loop. So I have to explicitly mention it. And then we can just write a loop and see how it behaves. I can write something like cout number of ways for I passes, is it? I passes is, and I can print answer of 5. I think this should be it. Let's try to run this. Enter the number of players. So we know the answer for 4 and 7. We had derived the answer for 4 and 7 in the first video using classical mathematical approach. So let's just try and verify that here. So we have 4 players, we have 7 passes. Answer after 7 passes is 546. Voila. And the beauty is, since we have written a general solution, machine can compute the value for any number absolutely. So let's say we have someone says that I'm not interested in, like, it was just 4 players and 7 passes. So we are able to do it by hand. Let's say there were 100 players. Let's say there was 2000 passes. I mean, this is an integer overflow, by the way. I mean, there is something called, we have to keep a limit on what can be the maximum value. So integer overflows do happen. This is a case of integer overflow. I can try to reduce it. We can try to reduce it. It will be better. This is a bit too much. So let's say there are 10 players. Let's say there are 20 passes. Yeah, this is more like it. In fact, here also we are having some integer overflow. The total number of possibilities is absolutely bonkers. It's going absolutely bonkers. Let me declare them as long. So these are just the kind of storage units we can use in programming in C++ to be specific. This is a C++ code. If I do that, will I be able to avoid overflow? Let's see. So let's say there are 10 players, there are 20 passes. Yeah, beautiful. This is the power of computing, my friends. Because let's say the actual problem had 20 passes and 10 players. By hand, it would be impossible to solve it. Or unless we use some other advanced algorithm. I am not aware of it. I don't think we could do it by hand, like using the standard approach that we followed in the part 1 of the video. However, if we build a more robust solution using recurrence and we write a piece of code, then the machine does the work for us. Any number of players, any number of passes, boom, you get the answer. So just going through the code once again, this code is literally what we derived over here. The same idea has been implemented. Just some programming paradigms have been taken into consideration. That's just how we have to structure code. Those are just the rules of programming, so to speak. Coming back to the solution once again, just for a quick recap, what we did was, in the original part 1, we solved it mathematically. Here we took general variables. And since we took general variables, the first part is to understand that answer after n number of passes is same as the number of ways the remaining players P1 to Pm-1, how many ways they can receive the ball after n-1 pass. Because, I mean, ultimately, A receives the ball finally from one of them, right? A receives the ball finally from one of those players. So this was the first part to understand. Once we understand that, we try to break this ways of n-1. That is, either P1 to Pm-1 received the ball from A, in which case each of them had an access to answer of n-2 contributions from A, and this is multiplied due to that reason because each of the n-1 players got those many contributions, or they received the ball from one among themselves, in which case this was the explanation for that. Each of them will be present m-2 times at n-2, like those will be their contributions. They will be present all the times except when they themselves are present at x of n-1. That was the idea. Taking m-2 common, we got this particular term, and hence this was the final recurrence that we built. Once we got the recurrence, we defined some basic values so that we can write our code. And then writing the code was just a piece of cake, a very standard code using a for loop was written, and we can see the result. That's all for today's video. Thank you for watching and stay tuned for more.